Okay, Laura comes from the Observatoire de Paris, and she's gonna review or talk about gravitational wave theory. Go ahead.
Okay, so can you hear me well? Yes. So I will speak about gravitational waves and mostly on theory. So it will be the only slide on the only talk on theory, I think, but it's to start. So I won't enter too much into details, but let's start. Yeah, so this is the observatory in Meudon, close to Paris. That is also very nice when there is sun. So just to start with gravitational wave detection, let me start with the first detection we had. So GW 150914. So it was like 10 years ago now. And so as you see, it was a very nice event. It was very loud, so we could see almost by eye. On the bottom, you can see the chirp. So I put the formula on the bottom, just the increase in frequency that you see just around close to the merger of the two black holes. And yeah, that's it. So it was very nice. It didn't require much modeling for this. I think only as we are seeing, as it was very loud, and we are seeing only mostly the merger, like just numerical relativity waveform were useful, but well, we were lucky. Since then, we have detected many events. One of them that is relevant for this talk, I think it's GW 17 on 0817. So the one, I think the only one where we have also the multi-messenger detection, so detection in in particular in the electromagnetic sky. And with here you see the gamma ray burst that you see at the same time. Yes, so this was very nice also, but and it gave us many information, both in astrophysics, like for the formation of binary systems, for nucleosynthesis of heavy elements, for the speed of travel of gravitational waves, all these kind of things, and for fundamental physics. So it was very interesting, and we hope that in the future we can detect more events like this, and I think that's why the ACME collaboration is for. Yes, and now, so this was the first detection. Now there have been the many. Let me go first to this slide, and then I will come back. So now there have been many detections on the first free run of LIGO and Virgo. You can see them and this is completely complementary to the electromagnetic observation of neutron star and black holes that you see at the bottom. And in blue, you have all the binary black hole detection that we have detected a lot of them with just the first free run. We have also a few merger of binary neutron star or neutron star black hole events. And now with O4, we are detecting, like I took this like a few months ago, but almost one event per day, or at least several per week. So it's very promising. There has been only one announcement so far, this one, and you can see that it tells us that we can still we still have a lot to learn with gravitational waves, because, for example, for this one, it's a merger of a neutron star plus a second object that is a bit too massive to be a neutron star and not enough massive to be a black hole. So we don't really know what it is, probably a small black hole, but let's see. And so by detecting more and more events, we will be able to constrain more of this, and that's why we are still interested in gravitational waves, I would say. So like I said, so then now the rest of the talk, I will try to explain you why do we still need to work on modeling gravitational waves, and in particular to have a very good bank of templates of gravitational waves. And well, I will speak also a bit of other things that I like, so because I like them. But just to start, why do we need the precise waveform templates? First, it's because like the signal for gravitational waves is, as you mostly know, is very low. It's 10 to the minus 18, and so it's hidden in the noise, and you need to find it. And for this, do some match filtering with a bank of using a bank of precise waveform templates. So I've put it, it's the expression like looking for a needle in a haystack. I have the French translation for you to learn. And I will give the answer of where is the needle at the end. But yes, so that's why we need very precise modeling and waveform modeling, and that we need to use different techniques also, because you can see that this one, for example, was quite long, many cycles. So it's numerical relativity. Yes. Also in the future, we will have new gravitational wave detectors. We'll have LISA in space, that is here. And we will also have Einstein telescope-like telescope in as the next generation of ground-based detectors. So you have Einstein telescope. In the US, there will be, or there should be, cosmic explorers. And so with this, we will be able to detect much more events at to noise ratio. And and so this is shown on this plot taken from the recent Einstein telescope blue book. Where that's where you can see the complementary between the two types of telescopes. So hopefully, if they, for example, are in work at the same time, at the same period, like around 2035, if we are optimistic, you can see that. So we have many different sources. We will have better sensibility than LIGO Virgo K-graph or Einstein telescope, with like going down the curve, sensibility curve going down, and in particular with lower frequencies. And also you will have new sources in LISA, like supermassive black hole binaries or extreme mass ratio in spirals. There will also be some events that are binary black hole or binary neutron star that we hope to see in both detectors. So you can see the very early on spiral with LISA, and then the merger with Einstein telescope. So this will be very interesting to follow up on this. But for this, we need to improve our current model of gravitational waves, because then the last thing that I can say that we will have superposition of signal. If we are detecting too many signals, they will be all superposed. And we will have to disentangle between the different signals. And for this, we need to come with new techniques, because that's not something that is happening at the moment. Yes, so that's gives me why we need to have a bank of extremely precise waveforms. The next question is, how do we do to have these waveforms? And why do we need to use different techniques? So the first is, as I said, we have very different sources that span. So I didn't speak about pulsar timing array, for example, but I think probably Antoine will speak about it later. So yeah, I won't mention much, but you see that we have very different sources. I mentioned the binary black hole, supermassive or not, but you can have also some supernova explosion, pulsars, all kind of things. So we need different techniques to model all these systems, and they will come also with very different type of waveforms or signal that you see. And I didn't mention the stochastic gravitational background or the more exotic source of cosmological origin that we could see also with our current or future detectors. To model this source, so these are, so as you know, gravitational waves is a prediction of general relativity, and general relativity is a very nonlinear theory. It's a very nice theory that looks simple, but is actually very complicated, and solving the Einstein equation, which is what we need to do to get the gravitational waveform, is very difficult, and so we need both numerical and analytical tools to do this. And so now I will give you a sketch of how we do this for the source I'm studying, and that are the main source for the interferometers that we are using, like LIGO, Virgo, or LISA. And so I'm considering mostly a binary system. But to do this, we need to solve different problems. So if we have the two objects, the first system that we need to solve is, what are my two objects? So this is a theory for modeling neutron star or black holes. So this is what's at the bottom. So just one single object. Then when they are in a binary, you need to describe the movement of these two objects, or they move. And finally, you go very far, so where we are, and we observe the source, and so this is the gravitational wave. And so these scales are very spirited, and it allows us to let's say, solve the equation step by step, depending on the region where we are. So the equation we need to solve is this equation, which is the Einstein equation. Yeah. And to do this, I will linearize my theory. So you can, different technique, I will come back to this, but one is just, I put it in the computer and I solve it. In practice, it's a bit more complicated, but that's it. But when we want, usually what we do is we do some assumption. And for this, we define the perturbation that I will call H from the metric. So it's the deviation from the flat spacetime. And if you do this, you plug it in the Einstein equation, then you end up with an equation like this that gives you just a wave equation. So this is my wave equation with some source. And the source is made of the matter field, so all that is the matter, the actual source of the system. And because GR is nonlinear, then you have also on the nonlinearities that I put on the right on the source. That tells me that actually the space-time is curved. And then you have a second equation that can be derived from this one, or not, but that is just the matter equation. So it will give us all the matter. So if you will use this, you can solve different dimensions. So the first region is the internal region. So in that case, you can solve using different technique, like just directly with this equation for neutron star or with effective field theory, integrating out the internal degrees of freedom. But what we want at the end, mostly for gravitational wave, it's to have an effective description of my source. And at first approximation, we use just the point particle approximation. So we are far enough to see it as a point particle. So for example, black holes, in that case, only with their mass. And so that's what we use. It's like if we add point masses. Then we can also add some more effect, tidal finite size effect, like spin. So if my if the object, like black hole are spinning to the effective action, or you can also add tidal effects. Like if the object can be deformed, then you can include this, and it will affect the gravitational wave signal. For example, spin will give, and tidal effects will the waveform. And next, so once you have done the internal zone, you can go a bit further, and you will first solve the near zone. And so it means like all the two bodies are moving with respect to each other. So I don't enter into the details, but okay, you just solve it. So you just plug this assumption here, the point particle in the source here, and then you solve iteratively because I'm doing some perturbation. So I'm not saying at the moment what kind of expansion. Well, it's mostly done for post-Newtonian type of approximation, but the idea is the same for other technique where you expand in the mass ratio, I think. And you solve iteratively first the first order where you don't have any nonlinearities, and then you add the nonlinearities. And so this will give you, for example, the two-body dynamics, so how the two objects move. And so you recognize the Newton equation, and then you can add correction. And all the thing of gravitational wave modeling would be also to compute these corrections. And finally, so we have our waveform, and you know that gravitational wave is a quadrupolar deformation. So at first order, it's just a quadrupole. So this is a quadrupole moment of the source, but it's just given like any quadrupole moment. And so the gravitational wave is described as a double derivative of this quadrupole moment. This gives the waveform. Then you can also compute the energy balance equation, so the flux, so which tell you that a way to link the dynamics of the system. So the energy that is emitted by the binary system is equal to the flux that is received at infinity. And this flux at infinity is given by the multiple moment at infinity. And it's given by exactly this formula here, where x is just the frequency, more or less. And so this gives you the flux. And from this, you can, for example, determine the chirp mass, etc. How the frequency will evolve, and which gives you the chirp mass, that the equation that I showed at the very beginning. You can also determine some evolution of the orbital dynamics, like the period decay. So what is directly used, for example, for pulsars, gravitational waves detected from pulsars. You can also determine how the eccentricity evolved. So if your system was in an eccentric orbit at the beginning, then it will quickly circularize. And so this we can determine it from this equation. And more interesting, gravitational wave modeling, you determine also the amplitude and the phase of the waveform directly from this equation. And again, we will want, so this is the first order, but we will want to add correction to it. And so this gives me, yeah, to the next, to the, how we will, what are the techniques to go beyond this leading order gravitational waveform, but how we get more precise waveform and precise enough. So this is what is shown in kind of traditional plot that you see here between the mass ratio and the separation between two objects. And so we need to combine all these techniques that you see here to get the full waveform. But first we need to solve depending on in which region of space or which sources we consider. So let me start with the beginning. And if you have asymmetric objects, so a small object, small black hole, stellar mass black hole, neutron star orbiting a very massive black holes, a supermassive black holes. So it is what is shown in this plot. So you have small object orbiting a very massive one. And so at first approximation, the small object is just following the geodesics of the big object. But then, of course, the small object is a black hole. It also curves the spacetime, and so it will modify this geodesic equation. And we need to include this modification and take into account this back correction, basically of the modification of also the small object on the spacetime. So that's what is called usually gravitational self-force. So this is the self-force of the small object. And to solve this equation, we use the small parameter that we have. And in that case, the small parameter is a mass ratio. So because we have a small object and a very massive one. And so we do an expansion in the small ratio, and we solve it order by order. In practice, the orbits can be very eccentric. So gravitational field is not always very small, because you can go small object at some point, it will be very close to the big one, and then it will go far. So it will orbit like this. So that's why we need to use this parameter, small expansion, and not the velocity. For LISA, it is known that you need to go to second order self-force to get the correct accuracy for LISA. So this is work that is being developed at the moment. It has been done, and you need first to solve dynamic, but also to get the waveform. It has been done if the big object is Schwarzschild. It has also been done for Kerr, at least in some cases, but it's more complicated if you have spin. It's always more complicated with spins. And then there can be some interesting features when you study this object, like resonances, and I think that's what I'm plotting here, and where you see all the trajectories that you can have. And it's very interesting because we'll see them doing many orbits. So it will be long-lasting sources that you can see with this. So this is the first model, and so this is what you can describe it. And if you look at this plot, actually it works for very asymmetric object, but it has been shown to be very good also if you go to not so small mass ratio. So even if the two objects are, for example, a ratio of 1/100, then the waveform derived with the gravitational self-force techniques is not so bad. So that's an interesting thing that gives you pull the blue part up to the equal mass ratio. And so this brings me to the equal mass ratio case, but when the two objects are very close, so that's numerical relativity. So in that case, I have more or less equal mass objects, and I'm close to the merger. So in that case, I need to solve the full equation because the gravitational field is strong, very strong, and the velocities are very strong. So it's a mess. I cannot use any assumption. And so we need to use numerical relativity tools. It's very complicated because Einstein equations are complicated. It has been done, and there are many different techniques now. but it's still very expensive, computationally expensive, and so we can only describe a few orbits before the merger. I think the best simulation at the moment are a few hundreds of orbits before the merger, while we need waveform that describe like much more orbits, like tens of thousands extra. There are also complications, like the simplest is to have two black holes not spinning, but of course you need to add spin, you need to have sometimes consider them on eccentric orbits, etc. Yes. And so this is a recent simulation that the people in Potsdam have done using the parameter of these recent events where we don't know. And you can see that it's a nice method because they are usually able to do nice movies. And nice plots. So that's for numerical relativity. Yes. And finally, let's say the last method is for for the inspiral phase of more or less comparable mass ratio, comparable mass objects. In theory, it can be also used for asymmetric objects, but in practice, as asymmetric binary system usually have high eccentricity, the gravitational field will be very, for high eccentricity, gravitational field can be very strong when the object goes close to the other one. So it's better, more precise for comparable mass system. And so in that case, I have two objects that are slowly moving and with a weak gravitational field. And so I can do an expansion in this slow motion and weak gravitational field parameter. Thanks to the virial theorem, I can say that they are of the same order of magnitude. And so this will be my small expansion parameter, that is called the post-Newtonian expansion parameter. At first order is a Newton equation, and then you add correction in V over C, that we usually say 1 over C. So that's more or less what I explained. I used as an explanation at the beginning. First order, you use point particle approximation, just the two masses. Then you add spins, tides, etc. So you can add tidal effect, you can add spin. Spin is more complicated. You can have the dynamic, but solving the dynamics, it will depend on the spin, the orientation of the spin. So it's more complicated to solve the equation, let's say, and also to get the waveform in that case. You need to consider different orientation. For aligned spin, it's okay, it's doable, but for non-aligned spin, it's more complicated, and because you can have also a lot of precession. But it's currently being done, and the current state of the art of this equation of motion is 4.5 and the flux 4.5 pn, so V over C to the power 9 for point particle objects. But then when you add spin or tides, so the tides are known up to next to leading order. So as you know, in GR, they start at 5 pn. So V over C to the power 10, and we add correction to this 5 pn term. So at second order, let's say. And for the spin, I don't know exactly the status. It's always complicated depending on the orientation, etc. But it's more or less the same order, probably 3 pn in some cases. But it depends on precision, align or not, etc. So now this gives you the method to describe my system in different stages, but then it's, for example, this is only valid for the inspiral, but not for the merger, and numerical relativity was just to the merger. So we need to glue together this waveform. I also didn't mention that then you need also to describe the post-merger phase, and this is done by doing some perturbation expansion also as a black hole perturbation theory. So you just deform, it's a deformation of a black hole, perturbed black hole expansion, and then you have quasi-normal modes, relaxation phase to a normal stationary black holes. Then to get the full waveform, we have different techniques. One is called surrogate model. I don't speak about them. They are mostly based on numerical waveform. And they interpolate between some numerical models. The difficulty with this model is that we need to some models that are very accurate, describe the full waveform from the inspiral up to the post-merger phase, but also that can be generated very quickly so that we can do the data analysis with them. So the first model is the EOB class of waveform. So in that case, it uses so the main ingredient is the two-body problem, so the dynamics of the in-spiral phase, the post-Newtonian waveform. And the goal is to improve them for them to be more as accurate also when you go to the merger. And so to do this, they just map the two-body problem to an effective one-body problem. So as if you have one object that is moving in a perturbed bilateral space-time. So you have a map to map my initial problem to this dynamics, and then there are tools and also mathematical tools like resummation to get the effective waveform. Yeah. In practice, this system, so it dates back from like it's more than 25-year-old now. It's how we got the first full waveform before numerical relativity results were obtained. And it allows to have the post-Newtonian valid up to much close to up to the merger. Now it has been refined. It takes ingredient for all different techniques and also for numerical relativity for calibration, but also from gravitational self force, post-Newtonian, like post-Minkowskian, so kind of more scattering amplitude information, and also for the post-merger phase from black hole perturbation theory. So all this works very well, and they are always refining the waveform with this. The other alternative one is a phenomenological class of waveforms. So in that case, you just take the post-Newtonian waveform and you just improve it by adding artificially in your waveform some unknown parameters that extend the post-Newtonian phase to take into account the unknown in our post-Newtonian terms. So for example, the 5 or 6 PN terms that are not known. And then you add an intermediate phase characterized also by some parameters, like for example, the beta here. So the 5, for example, are the post-Newtonian that are known. This one are the post-Newtonian that are not known. The beta are the intermediate phase, and then you have the merger phase. And so they do this, and they calibrate our waveform written like this against a few numerical simulations. They don't need many simulations, so that's good because they don't. Once they have trained it on some numerical simulation, they don't need to run new simulation, and they can have the full waveform like this. So it's a very nice method because it's once it's prepared, you can generate waveform for all kind of system very quickly. It's a bit less accurate than EOB waveform, but they are faster. So it's yeah, you need both techniques. This one is good because you can generate very fast. EOB waveform are usually a bit more accurate, but a bit more slow to generate. And then they compare between them to see if with the accuracy. And so currently both models are used by LIGO and Virgo to do the data analysis. Yes. And so this is the main tools that are used. Next, I will just say a few words about why we need to go beyond GR. This is because I like it. But it's also because, as you have seen, we know that TOGR is a very nice theory that works there. And I like it. It has produced very thing. It has not been proven to be explicitly wrong so far, but we know that we have some inconsistency anyways in some observation, in particular for cosmological observations. We don't know how to explain many things like dark energy, dark matter. We also don't have a quantum gravity theory of gravity, so that's why we need to test our theory. And so it can be done in different ways. The first one is with pulsars. So on the top you have like some constraint of some theory, like Bronsdicki-like theory, so just with a scalar field, massless scalar field coming from the observation of triple pulsars. It's more or less the most accurate result we have, and so they constrain this theory with a very good order. They have also been able to rule out some theories. Then you can do a gravitational wave test with LIGO and Virgo, and currently what is done is a null test. So we just test deviation of the waveform, so you allow for some deviation of the post-Newtonian parameters, and you constrain them order by order, so not allowing like one parameter by one parameter. So this is the result that you find. I think it was from the first two rounds of LIGO and Virgo. And you can see that the best constraint, so this one is for the dipolar radiation, that we don't see, that is not present in GR. So that's the one that is better constrained because we don't see it. And all the one are so this is a Newtonian order, then this is a 1 PN extra. And so it's, yeah, well, GR works well so far. But still, these tests, I think, they are limited because it's just null tests. So you allow for deviation, but only one parameter by one parameter. So it could miss some deviation in, like, it could miss the fact that in practice, if you have new theory, the deviation will be linked one to each other. And also, there is currently no systematic way to, if you detect one thing, there is no systematic way to link this back to a specific theory or type of theory. Let me mention that there has also been some full post-Newtonian or numerical relativity waveform that have been obtained in very specific theories that are listed here, like mostly in scalar type, scalar tensor type of theories, so where you just add a scalar field to GR. Again, doing the full machinery of waveform modeling for each alternative theory that we are is very expensive. Like, it's a lot of work, so we cannot do this. So we still need to have some parameters waveform, but we need a better models. And so that, like, I'm just sketching it. So that's what we can do, for example, by just, if you allow for curvature, a new theory with additional order in curvature, like cubic gravity or things like this, then we would like to have something that tells you how what is the PN order, and also how it scales with the new physics mass, so that you can use this information and the different scaling to distinguish between different systematic bias and the theory. And if you manage to have many detection with different masses, for different masses, you will be able to first distinguish from this new physics from systematics, and then if you manage to have the scaling, and in particular the post-Newtonian scaling, then you can trace back to some type of theory like this. And so with this, I'm concluding, just giving you back why we need precise modeling. And I hope that I convince you that we still need to work on the modeling and to have very good waveforms. And I give you the answer for the needle.
Okay, any questions or comments? Yeah, we have one there.
Hi, thanks for the talk. You touched on this briefly. Could you just describe a little bit more? How different do the techniques for waveform modeling for LISA will they have to be than for currently LVK?
So the main thing that LISA, well, if I go back to this, there are two things. So for the source that we know that will be just comparable mass black holes, I think the techniques that we have, in particular numerical and post-Newtonian and all the full waveform, they will be mostly the same. The only thing is that we will probably have to improve the accuracy, but that's it. So it's not much more, let's say, not much more work. The only thing that we will have new sources like extreme mass ratio in spiral. And these sources, we don't see them in LIGO because they are just for LISA frequency range. And this is where gravitational cell force step in. So far, gravitational cell force waveform were not used because we don't see the source that they are used for. But yes, for LISA, it will be important, and that's what so they are working on it, and they have a few waveforms, but there isn't a pipeline devoted to gravitational cell force and extreme mass ratio spiral waveforms yet. So that's the thing that has to be developed in the next 10 years quickly.
Any other question?
Thank you. It was a really nice talk. I really enjoyed that. Sorry, my ignorance, but I was actually wondering how many templates are used typically for matching, for instance, like with the LVK general relativity or with other types of gravity?
Well, so I'm not in LIGO Virgo, and so I'm not doing data analysis. So I don't know exactly the answer. I don't know the answer to the first question. I think the answer to the second question is that currently we have full waveform only for general relativity. This is the only way to test GR. It's with this agnostic tail test, just modifying, adding some parameter in the waveform, but that's it. For OMED, I don't know exactly how they do the data analysis with how many models, but probably some people know in the audience.
Anybody else know as well? Tens of thousands evaluations for an analysis.
So that's why you need to be able to generate them very quickly, probably.
Okay, any other questions? We still have a few minutes. If not, I have a question, but I would like to give space to other people. All right, I go. The first time that I see this plot with the eccentricity, which I find it quite nice. But I see a big hole at high eccentricity and equal mass binary. Is there any technique that can go there, or we are completely far away from?
So I should say that this plot is not completely accurate.
Okay.
First, because the gap here is, I don't think there is such a big gap here. Okay. So cell force should go in this direction. There have been a lot of work exactly at the between. So for high eccentricity is always complicated. So now there are these scattering amplitude techniques that are used and that can be mapped to high eccentricity system, event bond system. It's not sure that it works at very high accuracy, very high order. So scattering amplitude, they just do an expansion in the gravitational field, but not in velocity. So that's kind of orthogonal to post-Newtonian, but it can be used to like combination of these techniques. Then currently there are also a lot of work comparing or merging like scattering events with numerical relativity, and also scattering amplitude event with gravitational cell force. With eccentricity, I know that there is some problem of definition of the eccentricity, in particular in numerical relativity. It's not very clearly defined, I think. So it's different way of defining. So first, they need to solve this problem to be sure to compare the same thing, I think.
Okay, so it's more a problem of theory and, let's say, identify the right quantities than actually going there with the numerics, or?
Yeah, well, also, like if you add eccentricity to numerical relativity, you add a new scale. So you need to, it's more complicated to do highly eccentric numerical simulation, because then you need to resolve, you have, more, you need to add more resolution in some way.
Okay, great. If there is no last question, then we can thank again Laura.